All right, let's do a whole example from start to finish here. So in auto racing, a pit stop is when a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. So we're talking about racing, typically on like a long sort of oval shaped track, right? The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. A pit crew claims that its mean pit stop time for 4 new tires and fuels is less than 13 seconds. So it means that that team can change out 4 tires and refuel the car in less than 13 seconds. And you want your pit crew to be extremely fast, right? So you can get right back into the race. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19. Is there enough evidence to support the claim at alpha equals 0.01? And we're going to use the p-value method here. So go through your steps. I know I went through them on the page before, okay, in the last video. So you have your steps here, and I'm going to go right in order. So the first thing I'm going to do is I'm going to do my requirement check. I'm just going to call this a requirement check. So is sigma known? Yes, sigma is the population standard deviation, and it is 0.19 seconds. Is the sample random? Yes, it is random, right? So it is random. Is the population normal? Or is your sample size at least 30? So if I look here, I don't see anything about the population, but I do see my sample size is 32. So yes, because our sample size is equal to 32. So we satisfy the requirement check. Okay, the second thing I'm going to do now, I'm going to state the claim and identify the null and alternative hypotheses. So my claim here, so the pit crew claims that its mean pit stop time is less than 13 seconds. So the mean is less than 13. Now, this has no equal sign, so it's going to go ahead down here to my alternative hypothesis. And then the null is the opposite, but with the equality. So greater than or equal to 13. Three, what is your level of significance? That means what is your alpha? We are told here that the alpha is 0.01. Step 4, find the test statistic. So I'm going to scroll up in a second. I'm just going to write this formula down on my paper so I have it. So this is the formula for the test statistic. So my X bar here, so what is my X bar? It is sample mean of 12.9. So my X bar is 12.9. So I'm going to do 12.9 minus the mean. Now the mean is this one right here. So this is from the null hypothesis. You're going to use the equality version. So just the 13. My sigma is 0.19 and my sample size is 32. Okay. So I'm going to go ahead and plug this all into my calculator. And let's see. I get about negative 2.98. Okay. It is going to be negative because 12.9 minus 13 is going to be negative 0.1. And then we're going to divide that value by our denominator. Okay, so let's go back. What is our fifth step? Find the area that corresponds to the z. But I'm going to combine 5 and 6 together. I really think they do go together because you also have to keep in mind if it's a left-tailed, right-tailed, or two-tailed test. So you have to do kind of both of those together. So steps 5, 6. I'm going to draw my picture. Okay, now remember, we're doing z-scores now. So my center is at 0. And my z-score is negative. So it's negative 2.98. Now, because this is less than, so remember, less than is going to lead to a left. tailed test. And you're using the alternative hypothesis for this. So I'm shading on the left here. So this right here, this area, going to equal to my p-value. Now you can go ahead and use that table in the back of the book, or you can use your calculator here. So if we use our calculator, it's second bars, and we're going to use normal CDF. Now my lower bound here is negative 99999. My upper bound is negative 2.98, and I have my mean and my standard deviation. So lower bound, and then upper, and then mean and standard deviation. So I hope you're taking good notes on this page, because this is kind of like your guideline for hypothesis testing here. So let's figure this out. Let me get my calculator here. All right. So second bars, normal CDF. I'm just typing in my information. And let's see. I'm going to get about 0.00144. And let's see, your book is rounding to 4 decimal places. So 0014 here. This is going to be your value. Now, if you're not using your calculator, that's okay. So just for this one example, let me show you guys one more time. So you're going to go to that z-score table if you're not using your calculator. And we're looking at negative 2.98. So here's negative 2.9, and then 0.8 is right there. So 0.0014 is the area in that left tail. And again, your table always gives areas to the left, so it does match our picture. You just want to be careful with the z-score table. Remember that it only gives areas to the left. So if you need the area to the right, you'll have to subtract with 1 instead to get that correct value. All right, so that is part 5 and 6. And let's see. So now I have part 7 here. And it says, make a decision to reject or fail to reject the null hypothesis. So you're comparing your p-value and your alpha here. So my p-value and my alpha. My p-value is 0.0014, and my alpha is 0.01. So this is smaller than this one, right? If you're not sure, line them up. Okay. So if you need to, make them the same number of decimals and go in order. So this is both 0, this is both 0, this is 1, this is 0. So this one is bigger. So your alpha here is bigger, and your p-value is smaller. If your p-value is less than alpha, that's when, or less than or equal to, that's when you reject the null. So our p-value here is smaller than alpha, so we are going to reject the null hypothesis. And our last final step is to interpret the decision in the context of the original claim. Now, this is something where if you are still kind of figuring this part out, you can go back to your 7.1 notes. So I'm just going to find that right now. Okay, so about halfway through your 7.1 notes, we have this little chart at the bottom. So that can help you get started if you're struggling. So in our example, our claim was the alternative, right? So here, our claim was the alternative, and we decided in the last step that we are going to reject the null hypothesis. So if I go to that table, okay, I see the claim is the alternative, and I'm rejecting the null. So there is enough evidence to support the claim. And our claim here was the mean pit stop time is less than 13 seconds. So another thing you can do here, although maybe it's a little kind of funny, let me just rewrite our original problem here. And this was the claim. So we are rejecting that null hypothesis, right? We are rejecting the null. So we're basically saying like, hey, no, this does not look right. That does not work, doesn't work. So if we're crossing this one out, it's kind of saying that this one then must be true. Again, it's not a proof, but the data is leaning that way. So if you're not doing well with the table, kind of think about what's happening here. So if I'm rejecting the null, I'm getting rid of the null. So that means the other piece must be true. So we're supporting our claim here. We're saying like, hey, this looks like it's true. So we're supporting our claim in this case, because that's our claim, that the time is less than 13. So this is your process for how to hypothesis test. Now I have some minor technology here that you can use if you want, or you don't have to. So if you're not a technology person, you don't need any technology here except for some basic calculator skills, because you can use the table, that Z table as well. So, or Z table, which is table 4 in your book, if you prefer. Now, I will tell you that there is an even faster way to do some of this on your calculator. So for the example here, we kind of did most of it by hand, and we just did a little bit of calculator work if you wanted to. But you actually can get the test statistic and the p-value on your calculator at the same time, which is really, really nice. It just saves you some work. You still have to do the setup. You still have to do your setup. You still have to think about what kind of test you have. And then you still have to interpret the results. So that part doesn't change, but there is a shortcut way that you can get steps 4 and 5, 6 done in kind of one shot. And it's this right here. So we can also find, again, the test statistic and the p-value using technology. So these are steps 4, 5, and 6. To do this, you're going to do the following. So let me show you the last example we just did. All right, so we're going to press stats first. There it is, stats first. So right here, or stat, excuse me, stat. Then over the top, go over to test instead, and you're going to click the first one, which says Z-test. Now, here, there's 2 different ways to do it. So for me, you want to make sure you highlight stats on the bottom. That was a little hard to see here with the glare. Nope, that makes it worse. All right, so you can see data, and then here it says stats. So if you click data, it actually uses the data if you entered it in L1. So if you have a raw data set, you can enter your data in L1 and just hit data, and it will kind of fill in all those values for you. But most of the time, you're using MyMathLab, so you're going to have some of this work done. So you're going to hit stats, and then you'll be able to enter your different parts. So mu sub 0 is the hypothesis mean. So in this example here, it was 13, right? Because we were trying to show 13 seconds. So I'm going to type in 13. The sigma that we were given was 0.19. Now, X bar is your sample mean. So your sample mean, we said, was 12.9. N is your sample size, which is 32. Now, I'm not quite done. On the bottom, you'll see, so hard to see with the lighting. Oh, that makes it worse. Let's try to go further in. All right, you can see a little bit. So you'll see not equal to, less than, or greater than. So what they're doing here is they're looking for the alternative hypothesis. So basically you have to tell your calculator, is it a left-tailed, right-tailed, or two-tailed test? That's how they're asking. So our alternative hypothesis was a less than, right? So we're going to hit the less than key. And you will see that these go ahead and adjust. So your Z value there is negative 2.977. So negative 2.98, which is what we had in part 4. And then your p-value here is 0.00145. So when you round, you get 0.0015 instead of 0.0014. But again, technology is actually, this is actually the most accurate way to do it. You're right there, just like we got. So this is another way where you can kind of cut steps 4, 5, and 6 down. Just do it in one big shot. But you do have to know all your information to plug in, and you do have to make sure you tell it what kind of test you have, because that will change your results. You can see how the p-values are changing, right? The nice thing with the calculator too is you can't really see it here, but you do get a graph. You just can't, it's just too close to really see there. But it does actually kind of shade in for you. You can kind of see it starting to shade in the corner. So it does give you a little graph here too. All right, so let's do one last example. All right, let me kind of scooch everything over, line back up again. Okay, so let's do our last example. It says, according to a study of US homes that use heating equipment, the mean indoor temperature at night during the winter is 68.3 degrees. You think this information is incorrect. So you randomly select 25 homes that use heating equipment in the winter and find that the mean indoor temperature is 67.2. Now, keep in mind here, this is from the sample, right? So this 67.2 is your sample mean that we got from the 25 houses. This one up here is like your population mean, so your mu. From past studies, the population standard deviation is known to be 3.5 degrees Fahrenheit, and the population is normally distributed. Is there enough evidence to support your claim at alpha equals 0.02? Use a p-value. So first thing here is we have to do a requirement check. So remember, is sigma known? It is. Sigma is known to be 3.5 degrees Fahrenheit. So they've probably been doing research on this topic for a while, so they do have a good understanding of the population already. We have to make sure that our sample is random. Which it is, right? It says a random sample. And then we have to make sure either our population is normal or our sample size is at least 30. And we are told that from past studies, the population is normal. So I do know the population is normal, and that's good because my N here is only 25 because I'm only choosing 25 houses. But it's okay because I do have some prior data that shows the population is normal here. So we do want to be a little careful here. So our claim in this case is that this is wrong, right? So our claim is that the 68.3 is wrong. And they're saying that the 68.3 is correct, right? And we're not told that it's greater than or less than. It says is 68.3. So according to this other study, they're saying that it is 68.3. So we're saying that this is not true. It is not 68.3 degrees Fahrenheit. So our null here is that it is 68.3, and our alternative is that it is not 68.3. Okay. So like I said, this one's a little tricky because it depends on who is leading this discussion, right? So we're saying that, hey, we don't think this is right. So our claim is that this is wrong. This is not 68.3 degrees. So our claim is going to be, in this case, the alternative, and that it is not 68.3 degrees. Our alpha, we are told, is 0.05 here. And I need my test statistic. So I'm going to do this one both ways so you can see it with technology and without. So we're using, let's see, our x bar minus the mean over a standard deviation over the square root of n. So our x bar here we said was 67.2. Now the mean is the population mean, so it's whatever your value is here. So 68.3 over, this was 3.5, and then the square root of 25. So when you divide this out and multiply and everything, or sorry, subtract and divide, not multiply, then you get about negative 1.57. Now I'm using z values, so my center is at 0. This value is negative. And we're going to just double check this, right? So we're looking at not equals here. So this means that I have a two-tailed test. So you want to make sure you check, so it's two-tailed. So I know I only have the negative z, but there must be a positive z on the other side here to give that same cutoff, because I have to have two tails, one here and one here. So our probability, our p-value, is this one plus this one. So what we can do, because this is perfectly symmetric, is I could just find the p-value in one of them, and then that would give me, or sorry, the probability in one of them, and then I can double that. So if I want to use my calculator here, I'm doing normal CDF. I'm going to do just this side. My lower bound is negative 99999. My z value is negative 1.57. My mean is 0, and my standard deviation is 1. Okay. So I'm getting a value of 0.058207.6. All right, so rounding here to 4 decimal places, I have 0.0582. Now just remember that it's two-tailed, so you need 2 of these. So you're going to multiply this value by 2. And I get about 0.1164. So my p-value here is 0.1164. Now, if you're not using your calculator, that's totally fine. So what you're going to do is, again, just go to that table in the book. It's too big. So I'm looking at negative 157. So there's negative 15, and then I'm going over 27, and I see 0.0582, just like we had. And then just remember that you're doubling that because you have a two-tailed test here. So you need 2 of those. Think of it that way. All right, let me get my notes back out here. All right, so we have our p-value. Now we're actually ready to go ahead and test. So go up here for some more room. So our 6th piece here. Oh, actually, this is 5 and 6, sorry. So this is our 7th piece. So again, this kind of step here, this is 5 and 6 combined. So our next step is to compare our p-value and our alpha. So our p-value here is 0.1164, and our alpha is 0.05. Now this value is definitely bigger. So 0.11, that's 0.11 compared to 0.5, right? 0.11 is bigger. So this is bigger. Our p-value is bigger. So if our p-value is bigger than the alpha, you are going to fail to reject the null hypothesis, okay? So remember, if your p-value is less than alpha, then you reject. Or less than or equal to, sorry. If your p-value is bigger than alpha, then we fail to reject. So we're not going to reject the null hypothesis here. So the final piece then is to really state this in words. So let's just be careful here. Our claim is the alternative hypothesis, which was that the mean is not equal to 68.3. and we are failing to reject the null hypothesis here. So we're not rejecting the null. So if you're stuck, again, go back to that table in the last section. See if I can find it again. I don't know why I put it away. Right here, and you can use this to get you started. So here our claim is the alternative, excuse me, and we're failing to reject the null. So our claim is the alternative, and we're going to fail to reject. So there is not enough evidence to support the claim. Okay, so there is not enough evidence then to support the claim that the mean is not 68.3 degrees. And again, this is at the level of alpha is 0.05, so at 0.05 significance level here. All right, so another way to do this too, if you're having trouble with the table, is, I'm just going to rewrite this one more time. So that was our null and our alternative hypothesis. And again, we're going to fail to reject the null. So if you fail to reject the null, you don't reject the null. So you basically say you're keeping the null. Okay, so keep the null. So that means we're keeping this, which means that this is probably wrong. And that was our claim here, right? So again, we're saying we're keeping this, which means the other one must be wrong. So our claim must be wrong. So as of right now, based on the current data, there seems to be nothing wrong with the null hypothesis. So according to the study where they had the mean at 68.3 degrees Fahrenheit, it seems perfectly fine. There doesn't seem to be anything wrong with it. Now, again, I'm not proving that it's 100% true, but at this point I'm saying I can't find anything wrong with it. So we're going to leave it as is. So that's what's going on here. So if you find that table not as helpful, think about it this way. Kind of think about, okay, well, what are you accepting? What are you rejecting? And then use that to figure out how to do your wording. Now, one last thing, let me show you that other technology piece. So let's say you would like to do steps 4, 5, and 6 on technology at once. So what you're going to do is you're going to press stat, you're going to do tests, and you're going to do a z-test. So if I go to my calculator here, I'm going to press stat, going over to tests, and I'm going to do a z-test. Now I'm going to make sure that I'm not selected on data. I'm going to select on stats so that I can just enter my information. Now my null here was 68.3. My sigma was 3.5. My sample mean was, what was it? 67.2. My sample size was 25. 25. And you have to be careful here. So what was your alternative hypothesis? It was a not equal to. So I need to change that and select not equal to. And you can see your graph change. Now I have two tails, right? So if I just did one of them, then I only have one side or the other. So here I have a two-tail test, and which matches my picture. So it's kind of nice. It's still a good idea to draw the picture. And then once everything is selected, your z and your p-value should be correct here. So you can see the z-value is negative 1.57, which is what we had for our z-value. And the p-value is 0.1161. Now we had 1164, so, and that's again due to rounding error. Because to use this, we rounded our z-score to 1.57, whereas your calculator is using 1.5714, etc. But you can see they're very close. So 0.1161 is our p-value here instead of 1164. This is actually more accurate. So this is really the way to go. And for me, you're welcome to use either method. It doesn't matter. So if you want to do steps 4, 5, and 6 in one shot, you can use this z-test feature instead. The only problem is sometimes on the homework, they may give you your Z value, in which case you're going to have to find the area on your own a little bit more manually, kind of like we did some of those problems in 7.1. But if the questions just ask you to do the full hypothesis test, then this calculator can be really helpful because it's going to do a bunch of your calculations for you. You still have to interpret everything on your own and understand the setup as well, but it does help to save some time for steps 4, 5, and 6. All right, so that's how to use the p-value method for testing hypotheses for means when sigma is known. And again, like I said, I did break up this section to 2 parts. So the p-value method, I think, tends to be the more utilized one because it lends itself very well to technology. Like I just showed you, there's some shortcuts that we can use here to find most of our calculations. But in the next set of videos, we'll talk about a second method using the critical value method. Both of them start very similar. So you're going to see most of it is the same, but you'll see some different changes along the way. But we're going to start the same way there too, with still thinking about the requirement checks, also thinking about setting up our claim, our null, and alternative hypotheses. So those are all important steps no matter which method